Hi everyone, how you doing? It's it's Clara, and I'm doing another one of my science videos. And the video today, I am continuing my talk on superconductivity. Like I say, I'm the manager in the Centre for Applied Superconductivity in the Materials Department of Oxford University, and so here I'm going over some of the basics of what superconductors are and how that happens, how it works, and just generally hopefully some cool stuff. And I've actually got some cool little videos that I can show you today of some of the properties that I'll be talking about. Of course, I would love to be able to film them better, but I haven't been able to go in my lab for about 2 months now, and I'm not sure when that's going to change thanks to the current coronavirus lockdown that we've got going on. So anyway, that don't really matter. I've got some videos that, and I think they're kind of cool. So let's move on to it. Alrighty, so I've got my slide up, and so like I say, I'm going to continue my talk on superconductivity, but today what I'm talking about is the magnetic properties. So these are how superconductors interact with magnetic fields from, say, a permanent magnet or whatever. And I'm going to talk, there'll be another talk where we can talk about how we can use their interaction with magnetic fields. But here I'm going to talk about how they interact with magnetic fields. And this isn't necessarily any magnetic force that they're generating. Again, that'll be in another talk. So here we're talking about the superconducting properties, and so this is one of my videos straight off. So this is a figure of a track of magnets that we glued together in my lab. A whole bunch of magnets. There's a one pole on the inside and then the opposite pole on the two outsides. And we have a superconductor in a polystyrene cup, which we've cooled down. There's a little bit of liquid nitrogen in there to keep it cold, because we already know that we've got to keep it cold to have our superconducting magnetic properties, as well as our electrical properties. It's the same for both. And you might have seen videos like this where you've got your superconductor floating above or below a magnetic track. So, yeah, we don't need to watch it again, although, why not? It's kind of cool, right? I got to admit, it was fun building this, because we could play around with it. It's not perfect, but yeah, I love it. It's so much fun. All right. So let's take our superconductor. So this time, once again, I've put up these yellow balls, which I'm going to say are the atoms of our superconductor. I've not talked about what the material of the superconductor is, and that's not really important for this explanation. But what we have here is a classic superconductor. And so it's made up of all these atoms in different particular structures, as I said in my last video. And, you know, you've got the bulk, the purple things to signify the bulk, and then the yellow bits of the atoms, right? And then what we do is we introduce a magnet. And a magnet has a magnetic field, so it's not actually, you know, a straight dotted line as I've got it in the video, but that's just a representation of the magnetic field. So I think we know that the magnetic field will go from north to south, and they'll be all different shapes depending on the size and the strength of the magnet. I've just represented them here as straight lines just for simplicity. And so if we introduce our permanent magnet and, you know, we bring it close to our superconductor, the magnetic field lines, the magnetic field will just pass through the material. That's what we expect. Now, I'm not going to go into the properties of magnetism, but I think we know that some materials will become magnetized and some won't. This isn't what's happening with our superconductors at the moment. The field is just passing through the material. It's not becoming magnetic, it's just passing through it. But then, when we cool down our superconductor to the critical temperature, then what we find with superconductors is at the same point where all of a sudden they have zero electrical resistance, all of a sudden they expel the magnetic fields. So they basically, if you have a superconductor and you cool it down and there's a permanent magnet by, the magnetic field is kicked out of the superconductor. It cannot pass through the bulk material. And this is really, quite unusual. So if you imagine that you had a permanent magnet and you dropped a cooled superconductor on it, it would sort of levitate because there's this force where the magnetic field lines are bending out the way, and so it's not a repulsion per se, it's just that it can't move through. And this is what happens with classic superconductors, which we call type 1 superconductors. So in the last talk about superconductors, I talked about superconductors and high temperature superconductors. So that's depending on the temperature at which their superconducting properties turn on. But within that, you've also got type 1 and type 2 superconductors. So with type 1 superconductors, when they're cold, magnetic field lines, basically they're pushed out, they're expelled from the bulk, and they can't travel, they can't pass through it. Now, if we take a type 2 superconductor, whilst they are warm, so they're above their critical temperature, again, the magnetic field just passes through the system like nothing's up. But what happens this time when we cool it down is that the magnetic fields can pass through the superconductor, but they're pinned, they're squeezed, they're pushed. They can only go through the material in certain points. So you've got these points where the flux is pinned, and so that might be cracks in the grain, it might be imperfections in the structure, it might be a dopant or something like that. Basically, there's certain points within the material that the magnetic field can pass through, and so it gets trapped, it gets locked in place, and it stays where it is. Again, it's not becoming magnetic, but it's just interacting with the magnetic field lines, and it's locking them in a particular place within the bulk. So with the type 1 it was on the outside, and with the type 2 it's on the inside. Now I should point out that if you cool down a superconductor type 2 and there's no magnetic field in place, then it'll trap no magnetic field, which means no magnetic field can pass through it. It doesn't become type 1, it is different, but magnetic fields can't pass through. But if you cool it down in the presence of a magnet, which is what I sort of did here, this is as we're cooling it down in the presence of a magnet, and all of a sudden critical temperature, and we've trapped the magnetic field, and it's being forced through these particular points. So this is called, this is how we trap magnetic fields. It's called flux pinning. And what's really cool is that if you then, having cooled it down and you keep it cold, if you move the magnet, the superconductor and the magnet want to stay in the same relative position. Oh, I'm going backwards here instead of forwards, but so now if we remove the magnet, what we see is move the magnet and the superconductor goes with it because it wants to snap to that position. It doesn't want the flux to pass through it in a different position. It'll just move and they'll stay in the same relative position to each other. And actually you can overcome that force. So you can remove the magnet and the superconductor, but then when you put them close together, they'll snap to the same position, the same relative position to each other. And so that's how we get these really cool videos. So in the last video I showed this one. This is the basic track with the magnetic field, and the superconductor is able to pass along it. And it's able to travel along it because the magnetic field is the same. Looking at the screen, we're moving the superconductor in the same direction as the central pole, and so it's able to move up and down that central pole because it's the same orientation, but it's not able to travel to the side of it. It's not able to cross the lines of the outer magnets in the track. And so not only can you, float these magnets, the superconductors above magnets, but you can also do the same in reverse. So here I've actually got a plastic cup with liquid nitrogen and a superconductor, and below it I've got a magnet. So I cooled down this superconductor whilst that magnet was in place, and what we see is that once it's cooled and I lift up the cup, the magnet is trapped in place, but this time it's below, it's not above. So it's nothing to do with it sort of falling on it. It's not like a gravity type effect. No, it's a relative position. They're locked to each other relatively. And you can actually spin this as a circular magnet, so you can spin it, and it's just really cool. And you can give it a push and a shake, and it'll stay there. I mean, you can remove it with enough force, but it'll just stay there. Oh, and in fact, we can actually, if you rotate the magnet or the superconductor, then the other will come with it. It's really cool. You can basically go from having a superconductor, sort of appearing to float above the superconductor, above the magnetic track, to suspending below it. And like I say, it's not that it's suspended or floating. It is just locked relative to each other, and with a bit of luck, it's not the best video, but with a bit of luck, I've cooled down the superconductor on my track, and so I cooled down the superconductor and put it on top while the magnetic track was underneath the superconductor, and then I flipped the magnetic field over, I turned it upside down, and the superconductor stayed the same distance away from the magnetic track, but now underneath. And then, of course, because it'll warm up, because it doesn't stay cold at room temperature for very long without liquid nitrogen constantly keeping it cold, so it will suspend. But I think that's really cool. We had loads of fun doing this, just sort of whipping, seeing whether we could get it upside down and twist before it warmed up. Basically, it's kind of tricky to show, really. Yeah, so that's that. So I in my last video I talked about the once you reach a certain temperature you have zero electrical resistance, and in this I'm showing that at the same temperature for the material. So that temperature for the electrical and magnetic properties is the same for a particular material. So if you're talking about titanium nitride, then the superconducting electrical properties will kick in at the same point. The magnetic and the electrical properties will kick in at the same point, but that'll be a different temperature to materials that we have called BISCO, or the first superconductor that was observed at Mercury. They'll all have different temperatures, but the temperature at which they transition, the electrical and the magnetic properties go at the same time. I think that's pretty cool, but maybe that's just me. So so that's another video on superconductivity, and I have got more videos on superconductivity coming up. So I'll talk more about the applications of them, and I'll talk a little bit about how we make them and things like that, and also maybe look a little bit at the history of superconductors. I think that could be kind of cool, and talk about some of the different materials that we use and the temperatures at which they superconduct. So yeah, exciting stuff. I will continue with superconductors for a little while, so hopefully you're enjoying that. And until next time, take care, and I'll see you soon. Bye.